So welcome to lecture 14 of MCS 471, numerical analysis. So today we start another chapter. We are considering interpolation. So today we define the interpolation problem. And we give examples. The interpolation problem replaces a difficult function by a polynomial. Or also it may be that we have some observations, we have data points, and we want to represent the data by a polynomial. So there are two sub-problems. We may be interested in the full coefficient vector of the polynomial. So that is the coefficient problem. To solve that coefficient problem, we will see the basis of Lagrange polynomials, so also called Lagrange interpolation. In some situations, we actually don't really care about the coefficient vector of the polynomial, but we care about the value. And the value problem can actually be solved faster than the coefficient problem. All right, let's then dive in. So what is the interpolation problem? So what we have are data points. So the data point could be from the evaluation of some function. What is important is that all data points are actually distinct from each other. So that will be an important condition. Then the output is a polynomial that interpolates. So here you see the interpolating condition. Now we have a polynomial of at most the number of points minus 1. In a way, we have already encountered this problem when we looked at the secant method. So we had 2 points and we were constructing the line through these 2 points. 2 points, degree 1 polynomial. So there is some terminology. So the polynomial interpolates the function at the interpolation points. And P is then also the interpolating polynomial. The little words actually matter often. So we will show that the interpolation problem, if it is well defined meaning that all the data points are distinct from each other, that there is a unique solution. So we can talk about the interpolating polynomial. So the first part of this lecture is mainly concerned with demonstrating the uniqueness and the well-definedness of this interpolation problem. Then the rest of this lecture will be considering two different methods. So in the first part, we will see that the solution, this interpolation problem, can be solved with linear algebra. And we already know how to solve linear systems. But the key point here is efficiently, how to do this efficiently. We will see that the value problem in particular can be solved in quadratic, with quadratic cost, quadratic in the dimension n. All right, so here is a motivating example. So we have the sine function, and we have 5 interpolation points. So the 5 interpolation points are marked by the dots. You see the plot of the blue sine function going from minus pi to pi, and the red curve is the polynomial that passes through these 5 points. So at these 5 points, the polynomial takes the same value as the sine function. You can see that the shape of the polynomial is about the same as the sine function. So if we would be interested, and we will be later on, if we were interested in the integral of the sine function, of course we know the antiderivative, but suppose that we do not know this, then we can compute or approximate the area between the red polynomial and the horizontal axis. So we will use interpolation when it comes to numerical integration. So with this plot, I mainly want to show the solution, or a solution with an example, a solution to the interpolation problem. What is the degree of the polynomial? Well, we have 5 points, and this will be a polynomial of degree 4. So there is a notebook that is posted, and it actually will show how to construct that polynomial. But I could also leave it up to an exercise here. All right, so we have the coefficient problem. So the coefficient problem asks to compute the coefficients of the interpolating polynomial. So we have the unknown coefficients. So here they are all written out with the dot, dot, dot notation. So we have n plus 1 coefficients. So the I is ranging from 0 to n. Observe that this might be a well-posed problem. We have n plus 1 input points and n plus 1 output points. So the size of the input matches the size of the output. That's a good sign. So we will prove the following theorem. If the interpolation points are all mutually distinct from each other, so we have no duplicate coordinates, we have no coordinates, we have no duplicate xi values, then we have a unique solution to the problem. And we can therefore speak of the interpolating problem. And that will essentially give us the first method to solve this problem. Setting up the interpolation conditions will lead to a linear system, showing that this linear system has a unique solution under the condition will actually prove the theorem. So it's a constructive proof. First step is to set up the interpolation conditions. So when I made the plot for the illustrative example on the second slide, I used the 5 points. So here we are using the dot, dot, dot notation. But for 5 points, this gives rise to 5 equations in 5 unknowns. It's not entirely clear. Typically, we have the x for the unknown. Here, actually, we have the unknown. We have the unknown coefficients. So what is given are the function values and also the points. So we have the n plus 1 points with corresponding function values. What is not known are the coefficients. So I will underline them here, or circle them. The coefficients are actually the unknowns. So we have the n plus 1 coefficients and the n plus 1 points xi and the corresponding function values fi. So it is important to know this starts out to be as a nonlinear problem. We want to compute a nonlinear object, a polynomial, but actually if we know values for x naught, we also know values for all the powers of x naught. So what looks here as a nonlinear system is actually just a plain linear system. So just knowing what the unknowns are. So they are the coefficients, and the coefficients appear linearly in this system. So the interpolation conditions are linear conditions. So the key conclusion here of this slide is that this is a linear problem, a linear system. And this is something that we know already. We put it into matrix vector notation. So all our linear systems are in matrix vector notation. This separates the coefficient matrix, the numerical coefficient matrix, and the numerical right-hand side from the unknown values of the linear system. So this is the same problem written down in matrix notation. So we have actually now a first algorithm. If we very constructively, we can solve linear systems. So problem solved. Not quite there yet. We have to still show that under the condition of different interpolation points, we actually have a unique solution. So this is a mathematical part. How do we prove that a system has unique solution? Well, it all depends on its coefficient matrix. If that coefficient matrix is a square matrix, as many rows as columns. So the coefficient matrix of the interpolation problem has a special name. It's called a Vandermonde matrix. So, and that Vandermonde matrix has a very special structure. Remember when we looked into linear system solving, most interesting problems actually always have structure. And the game is then always, can you solve the linear system in a cost that is less than cubic in the dimension? And the answer is often yes. So the game actually is a game that we can win and that we will also play here. So not losing sight of what we want to accomplish in this first part. Is this problem now well determined? Is there a unique solution? And yes, there is. So from linear algebra, we know that if the determinant of the coefficient matrix is different from 0, then our linear system has a unique solution. And we will set out to prove this. This is actually a linear algebra exercise. And if you took a linear algebra course, you may actually have encountered this exercise. So one can prove this expression by induction. Or you can actually, if you know the formulas for the expansion of determinants, you can see that this expansion will lead to a polynomial that is defined by all mutual distances. So it's a polynomial here for the example is probably best to look at. So if you look at 4 different points, then we compute all the mutual distances. So I will not leave this proof as an exercise, but it's good to see that the condition actually is very nicely expressed here. So the condition that all the interpolation points are distinct from each other. So we have a high degree polynomial, quadratic in the data points. So typically we don't really compute this high degree polynomial. So the theorem is then proven. So if the interpolation points are all distinct from each other, then the interpolation problem has a unique solution, and we can talk about the interpolating polynomial. All right, then. Now, this was the mathematical problem solved. But in numerical analysis, we actually care about the numerical hardness. So if something cannot be zero for it to work, then it often goes wrong as well if the numbers that we have are close to zero. And the condition of this interpolation problem can be illustrated with the simplest case. So that's actually also, again, the secant line problem. So if you have to construct a line to 2 points, so think about if you have somewhere a ruler and you want to balance the ruler on 2 fingers, your index finger at the left hand and your index finger at the right hand. So you need 2 hands for this exercise. So then that balancing of the ruler is very easy if your fingers are very far apart. It starts to get very tricky if you move your index fingers close to each other. So here actually we have 2 interpolation points that are very close to each other. So at the left, in the well-separated case, if you make small changes to x1 and x2, your line will move a little bit up or down. If you make little changes to x1, x2 at the right, then the slope of the line will actually change dramatically. So the output, here the simple line, is very sensitive to the distance of the points. So we will not continue this part in this lecture, but where we choose our interpolation points matters for the condition problem. Here is the van der Monde matrix. So also one reason why we actually are not solving the linear system directly is because these van der Monde matrices, so here is a very small system, dimension 5, it already can lead to a lot of 3-dimensional places. As we have seen, the condition number, actually the size of the condition number, so from the previous chapter, we actually look at the magnitude of the condition number. So that magnitude actually indicates the potential loss of decimal places. With this slide, I want to indicate the making of the van der Monde matrix. So we have our vector of points. So here the points are all equidistant. So we have an interval 0, 1, and we will subdivide this in 5 equal spaces. So it's actually here not that equal. So I have the first point, which I still label with 0. I have the second point, the third point, the fourth point, and actually I have now 6 points. So actually I should have cut off over here. So this gives me the 5 points at the same distance, 0.2. You see how the van der Monde matrix gets constructed in a double loop. And we compute all the powers of the points. So you will use this code in the following experiments. So for 5, we already lost 3 decimal places. What happens if you do this for 10, 20, and 40? So running the code on the previous slide is already the first problem is half of the exercise, then actually you use the fundamental inequality that we have seen in the previous chapter. So with 64 bits floats, we may assume that everything is correct to 16 decimal places. Now, in order to get an accuracy of 8 decimal places in your coefficients, you actually cannot afford that the condition number increases above 10 to the power 8. So for these dimensions 10, 20, 40, is there actually a dimension, is there a condition number larger than 10 to the power 8? That's actually what this question asks. So the purpose of this exercise is exploring the limits of the solving of the van der Monde matrix as a solution to this problem. So we do have a mathematically very satisfying solution to this problem already, but it's not efficient, so it's a cubic cost, and as this exercise will show, it's also actually not a very reliable method. It will not give accurate solutions. So that is the motivation for the two methods that we will now consider in the remaining part of this lecture. So the first method is Lagrange interpolation. We will not use the classical basis for polynomials. So the basis of the polynomials is 1, x to the power 2, x to the power 3. That is actually not such a good basis. So we will later in this course work with orthogonality, and actually one better uses another basis. So the key point of Lagrange is actually to change the way how we write our interpolating polynomials. And what Lagrange tells us, well, look at a simpler problem. Look at the problem of interpolating 1 and 0s. So the Lagrange polynomial are very special polynomials, and they solve this for a very special type where at the Lagrange polynomials there actually are kind of switches. They flip on or flip off. The ith Lagrange polynomial is 0 at all the interpolation points except the ith interpolation point. And that is accomplished by this form here of the Lagrange polynomials. So they are polynomials of degree n, and you make all the differences. So in the numerator here, you see that you make all the differences of x with all the other interpolation points. So in this loop here, you exclude the ith point. So the numerator actually implies that all the at all the other interpolation points, the ith Lagrange polynomial will vanish. So that satisfies this condition here. The other condition that you have a 1 is satisfied by the denominator. So we divide by all the differences of the ith interpolation point with all the other interpolation points. Again, skipping the ith one, and we know that all the data points are actually mutually distinct. So that's again an important condition for it to hold. Now, why consider this problem? Well, the point is that we can actually now consider the Lagrange interpolating polynomial. So what this form does, it separates the function values from the Lagrange polynomials. Namely, it actually separates the function values from the interpolation points. So separating where we interpolate from the values at the interpolation points. So often in applications, it so happens that you sample data at very fixed points. So every morning you do a reading of something. You read the temperature or you check your weight, and that is a fixed fixed value for x. What is changing is the temperature that you measure or is the weight. So in a way, you compute your Lagrange polynomials only once and for your fixed mutually distinct points. If you do this in the 7 days of the week, you actually have 7 data points. You have a polynomial of degree 6. And you compute your Lagrange polynomials once and for all. Your Lagrange form actually then only differs with the coefficients. So actually also observe that the coefficients actually of the Lagrange interpolation points are actually your FIs. Very good. And actually, the most important, the punchline now is that if you look at the flips, the on and the off of the Lagrange polynomials, you can see that if you plug in any of the interpolation points at the ith point, or say at the first point x0, only the first term appears. So you can see that if the Lagrange polynomial satisfy that 1,0 condition, that the polynomial that you make p of x will actually interpolate. So Lagrange interpolation provides a very nice solution for the coefficient problem. Here is an example. So I have the general formula of the Lagrange interpolating polynomial, and we evaluate the interpolating polynomial at 4 points. So we have the Lagrange polynomial L1. So actually, this is the second Lagrange polynomial. Here you see its shape. And you can verify that if you evaluate the Lagrange polynomial, that it will satisfy these conditions. And I've actually explained everything what is on the slide already. So the convenience is that these Lagrange polynomials here, they can remain fixed if the xi's stay the same all the time. All right, so the Lagrange interpolation solution is actually solving the Lagrange problem, the interpolation problem for a specific data set. Okay, so here is a theoretical exercise that will, so there is a hint that will require you to first write down what it means that the interpolation problem has a unique solution. So we consider an interpolation problem where we interpolate the constant function 1. So the constant function 1 is interpolated, and the interpolation problem has a unique solution. So if we interpolate the constant function 1, which is a polynomial of degree 0, then that is already the interpolating polynomial. And the interpolating polynomial, so I will write it now, so the Lagrange interpolation, you actually multiply the Li's with the Fi's. So what you have to show at the left is the Lagrange interpolation form of the specific problem. So if we have to show that the sum of the Lagrange polynomials equals 1, then we start by observing that the left-hand side is the Lagrange interpolating polynomial. The right-hand side is the interpolating polynomial. So 1 is a polynomial of degree 0, which is the lowest degree polynomial through these points. If we would solve the interpolation problem and we would find a different polynomial at the left other than 1, then actually that would have violated the theorem that we have just proven. So therefore, the two lines actually solve that exercise. So to solve that exercise, what you need to do is to rephrase the sentence here in a more elaborate way, as I explained to you, using your own words. So we will look at the Lagrange polynomials. All our algorithms are defined as Julia programs. So for this definition here, we use the package polynomials. So if you are starting with a fresh installation, you may have to add this. So the polynomials package is very convenient to convert coefficient vectors into polynomials, or to define polynomials from coefficient vectors. And we can multiply polynomials. So with this function here, that function returns the ith Lagrange polynomial by following the mathematical definition. So we look at the result. So we build up the polynomial each time. So this is here the minus xi. So that is the first coefficient plus x. So remember, we define polynomials as their coefficient vector written backwards. So we write the polynomials here with their coefficient vector. So the polynomial here is the polynomial x minus xi, where the xi, the coordinates of where the values for the xi's are in the array called PTS, are in these points. And notice the symmetry. We divide by the difference between the ith value, so given by the x here, with the ith point. So this is xi. So we skip in this loop here. So this is actually a single loop where we actually skip the ith term. So the term defined by the idx. So as an alternative, we could have used SymPy other than the polynomial of the polynomials package. But this is a very convenient way to do. And we want to verify whether the property that I just explained, that the sum of the Lagrange polynomials equals 1, we will actually verify this on a very small example. Here you see, when you run the program, that the interpolation conditions are met. And if we sum the Lagrange polynomials, then actually we might be a little bit surprised. We actually don't see 1. But notice the coefficients. So we always read our floating point coefficients from right to left, and they are written in scientific notation. So these numbers are actually very close to machine precision. So this is the solution of a very specific interpolation problem. Notice that the coefficients of these Lagrange polynomials start to be larger, but in practice you will actually never expand them again. So you don't really expand these polynomials in the conventional basis. So you leave them in the form of the Lagrange polynomials. So you can also see that we use interpolation to get the values in between the points. So as we take differences in between, it's kind of indicating that the numbers can actually not rise too much, especially if you take equidistant points. So this is already kind of an indication that the original problem, not if you see it via the van der Monde matrix, but if you see this in a proper basis as a proper problem, that the condition is not that bad. So that is actually what this problem asks again. So now see what happens if you now consider higher and higher degree polynomials. Will you still observe very small coefficients here? So which actually explains why the conditioning of the problem. So notice also from a linear algebra perspective, we are solving a structured linear algebra problem. So in our condition number estimates, we assume that all the coefficients can be changed independently. So we have n square inputs at the general condition problem. But actually the inputs for the interpolation problem are actually n plus 1 numbers. So the size of the data, the dimension of the data is actually linear, not quadratic. So that's also an indication why the interpolation problem might not have been that bad as we looked first at exercise 1. All right, we have solved the coefficient problem. Now notice that the coefficient problem still requires you, if you are going to write down all your Lagrange polynomials, that this still looks very much quadratic. So these are polynomials of degree n, and actually we have n plus 1 of them. So this still very much looks like a cubic problem somehow, or actually not, I'm sorry. So evaluating one Lagrange polynomial requires 2 times n multiplications. So it is actually a quadratic problem as well. So that's something that I should have pointed out. Now we can solve this still better if we are interested in only one value of the interpolating polynomial. So this often happens. We have observed data points and we want to see what is the in between. So linear interpolation evaluates the action at a line. So here we define this in full generality. So the value problem asks not for the polynomial, but asks for a number, the value of the interpolating polynomial. So we are interested, so in a way this is a local problem. We may have many data points, but we are interested only locally for some value. And that x star is typically different from all the other points. Now we will solve this problem recursively, proving the following theorem. So we will prove that if you want to solve the interpolating polynomial through n plus 1 data points, then that can be solved by interpolating the interpolation through the first endpoints and then through the last endpoints. So we can see this symbolically, but everything is done here via numbers. So this is and you recognize also the simplest form of Lagrange polynomial. So if you want to do linear interpolation a la Lagrange, then this is the formula. So what you do is you look at the last point, which is all the first point, and with linear interpolation you only have two, so your last point is actually the second point. And then one can verify that this theorem actually holds for 2 points. So this is a recursion, which will be, and the theorem will be proven by induction. So let's prove this. So we write down the formula. Notice that what is missing here is the last point. So the last, we end here at n, and what is missing here is the first point x naught. So notice the symmetry in this. So if you are proving this, so we prove first that the polynomial interpolates. So we just put the endpoint. So if you have only 2 points, so in the base case actually, then the formula is true. So that's the first bullet point here. In the first bullet point, you verify that if you plug in x naught, then the second term drops away because you're making the difference in the numerator here between x minus x naught. And then actually you use the induction hypothesis that the p naught up to pn minus 1 interpolates. So that is actually f naught. You do the same for xn. Then you verify for all the other points. So, I mean, here I give the proof in full generality, but the first bullet is actually also the base case for 2 points. And you see, if you solve actually the 2-point problem, the 2-point problem actually gives you the extremal points, the 2 special cases at x0 and xn. Then we prove it for any point that is not the first and the last. And there actually we do have to simplify the expression when we apply the induction hypothesis. So we apply the induction hypothesis that the polynomials here, that they actually interpolate. And then we follow from the simplification that this interpolates. All right, how does this, what is this now useful? Well, this gives rise to an algorithm where the quantities in the theorem are put into a table. So we compute P0 1 via interpolating x0 x1. Then we compute P1 P2 and then P2 P3. So here then we have the first column that is actually applying linear interpolation. Then we apply the recursion, we interpolate, now actually looking at the extreme points. So the x0 and the x2, we say that x0 has the value p0, 1, and x2 has the value p1, 2. You could also say that we always apply linear interpolation. So we continue doing that. And what you see in the end, so there is a benefit to it. We interpolate at an increasing number of points. So first we only consider the first 2 points, then the first 3 points, and then the all points, all 4 points. So what we actually interested in is the diagonal. And as soon as we have used f1, we can replace f0 by p01. We replace f1 by p12. So we can actually afford to replace. So this is a 2-dimensional table where we can actually be more efficient. So in the organization of this table, there is a linear algorithm here. We will not do this in linear cost, but the space can actually be linear. So we essentially replace the points that we compute, so P01, P12, P23, we replace this what I here circled by the diagonal. So it's kind of a folding up of the table. All right, here we have the mathematical algorithm where we still use these complicated notations. So it is also, again, the full interpolation problem stated. So we have the given interpolation data, and what we here express are all the intermediate numbers. So what the intermediate numbers imply is actually a repeated application of the theorem. So we do a repeated recursive linear interpolation. And we have an efficient memory usage if we relabel the points. So we store the points in arrays. So it may go rather fast here because we have seen the problem only at the very beginning, and now actually we already think about efficient algorithm. The point is that the cost is actually n squared. So you recognize the double loop. So the last loop doesn't go through the all end, but actually if you look at all the multiplications that you do, so we do 2 multiplications, 1 division, and a number of divisions that we can also save essentially, the cost will be quadratic. So we are solving a linear system essentially in quadratic time. So the problem, as we started out with the van der Monde matrix, looked like a cubic cost, looked to have a cubic cost. But here we actually have shown via this algorithm here, which is correct of the theorem, that we do have a quadratic cost algorithm. And the algorithm is actually codified in a Julia function. So we have the inputs, the x and the f, and then the x star, which is here represented by the xx. And there is a simple example for this. Again, you could eventually use the example of the sine function with the 5 points. See, with Neville's algorithm, we are a little bit more efficient. So all the differences with the x star, with the xi, instead of turning this into a quadratic computation, we save it in one vector. So this saves us some differences. So the differences that we do here, otherwise we would have a quadratic number. Well, actually, we still have a quadratic number, but we actually save some differences. So this is a very efficient algorithm. Efficient both in computations and also in terms of the memory. So here you see the storing of the result. And the result, the P, is not now a polynomial, but it means that we have the consecutive, hopefully more accurate values for the interpolated data at more and more points. So the I minus j plus 1, so as we get to I equals n, and we get larger and larger, you can actually see that the answer will be at the first position. So the last number that we compute is with j equals n, and that's at the first position. So here I have to remember that Julia arrays, they start at 1. All right, one last algorithm. What is now the cost of Lagrange interpolation? So suppose that you have to construct all the Lagrange polynomials. So we use the polynomials package. But suppose that you would not want to use the polynomials package. What if you would actually evaluate all the Lagrange polynomials at x star, and then you would also evaluate the Lagrange form? So you would multiply the evaluated Lagrange polynomials and function values. What is the cost? Is it quadratic? Is it cubic? All right, I will stop here. We continue in the next 3 lectures exploring interpolation.